So our next speaker is Professor William Tang. William Tang is a lecturer with the rank of professor in the Department of Astrophysical Sciences at Princeton University. He is also a participating faculty at the Center for Statistics and Machine Learning, an executive committee member for the Princeton Institute for Computational Sciences and Engineering, and principal research physicist at the Princeton Plasma Physics Laboratory, where he served as the chief scientist from 1997 to 2009. Professor Tang is recognized for his pioneering contributions to fusion energy research, accelerated by high-performance computing and deep learning. Let us please welcome Professor William Tang onto the stage.
Great, thank you. Okay, great. Thank you, Scott. Good morning, everybody. Great pleasure to be here. It's a great honor to be here. Before starting into this presentation, titles up here: validated AI-powered machine learning for accelerating delivery of scientific grand challenges going forward. First, a few words about Sidney Fernbach. I'm very humbled about receiving this award following a number of other tremendously distinguished scientists in this area. Sidney Fernbach was a pioneering computational physicist who founded the National Magnetic Fusion Energy Simulation Center, and which is the predecessor in California now at the Lawrence Berkeley Lab for NERSC, the National Energy Research Supercomputing Center that's located at Lawrence Berkeley Laboratory. The 2024 award can be viewed as a tribute, certainly to Professor Fernbach, but also to both the legacy of magnetic fusion energy research and for NERSC itself. So let me start off here with, this is a little bit of a dense sort of a graphic, but it captures what we're trying to go through. Basically, what are you doing all of this for? What kind of software is being developed, and what are you trying to aim for? And this is a foundational work for the so-called Scientific Discovery through Advanced Computing program that was established quite successfully some time ago. It's really, this figure here gives a measure of the state of understanding of natural and engineered systems. And so you start out with theory and a data-based model, and you put together computational physics surrounded by applied math and computer science. Everybody here should know about these things. And this is all integrated together, and you go through this workflow that I'm about to explain to you. On the one side here is the so-called validation loop. This is extremely important because you want to make sure that what you're putting forward correlates with reality. And so this is what we call the verification, validation, and uncertainty quantification loop. You repeat that over and over again. On the other side of the loop is the performance loop. That's, you can't wait forever for the software to be exercised, and you go through this loop again and again. Let me explain to you a little bit more about both of these loops. The validation loop here basically covers things like you're comparing against what? You're comparing against like simple empirical scaling, you carry out sensitivity studies of measured spectra, correlation functions, and so forth. And you keep on testing this and seeing just how realistic the information is. On the other side of the loop, the performance loop, you go through things like that evolved since the beginning of the program, which is the whole issues of so-called co-design, where you have interactions with the design engineers for supercomputing systems and so forth, and evolving into many other very exciting sorts of developments, including challenges like low memory, low locality, latency, and so forth. But in more modern times, the AI, deep learning, machine learning advances, which are explosive and very exciting. Anyway, you repeat these loops over and over again, and it's not static. You know, you're never ending this sort of thing, but you're getting better and better tools, and you repeat the cycle as new phenomena are encountered. So now focusing a bit more on one of the major grand challenges for the world, one of the things that I'm really going to focus on here is challenges associated with delivering clean energy, fusion energy that's been around for some time. I'll start out with some comments here about the situation analysis that it's truly an international enterprise. In Europe, the so-called Eurofusion Joint European Torus experiment is a very impressive experiment. They achieved 5 seconds of confinement time that they captured the hot thermonuclear plasma for a significant period of time so that it is relevant to this international thermonuclear energy reactor, this multi-billion-dollar device that involves many international countries, and it's located in France. There's, because of the pandemic and various other things, there's significant delays for this, and but Eurofusion delivered some really significant results using the actual nuclear fuel, the deuterium-tritium fuel. Then in more recent times, in the US, there was a major initiative that was launched by the White House, developing a so-called bold decadal vision for commercial fusion energy. And the focus there was to deliver so-called fusion pilot plants. These are actual devices, and well, ITER's a major device to go to, but this supposedly will happen before then. And as I said, this whole enterprise of delivering clean energy power for the world is a major, major initiative that everyone is interested in, major grand challenge. And China is very engaged in these areas. They have put forward plans for a fusion engineering so-called test reactor that's targeted for around the 2035 timeframe, similarly to what this US decadal grand challenge is supposed to be moving forward to. What is this all aiming for? The scientific goal is that you're trying to confine this hot thermonuclear plasma for a sufficient period of time for energy to be released and efficiently, and achieving the so-called triple product of density, temperature, and confinement time for a sufficient period of time for you to achieve what you're aiming for to deliver viable fusion power. This is there's been good progress towards this, and I'll talk about this, but what about this huge area of artificial intelligence, machine learning? There's a big roadmap for progress in this area in the US. It's called the FAST program, and prior to that, there was a lot of work that went into setting the template, if you will, and the targets for what you want to do here. And the aim here is to harness the power of AI in scientific discovery initiatives to move things forward. And here's a bit of a picture here of why this is an exciting time for fusion as a so-called final frontier of sustainable clean energy for the world. It's a little illustration of the sun. This is the same reaction by which the sun produces its energy, and we're moving closer to this. On the left-hand side here, you see this really impressive achievement using a laser fusion-based approach, inertial confinement, at the Lawrence Livermore lab. They achieved fusion break-even after 30 years of effort in this area in late 2020. It's a truly impressive effort. However, major grand challenges remain, because to deliver power on the grid for people to use, this remains a huge challenge that still needs progress. Now, with respect to magnetic fusion, which I'm personally much more familiar with, The Eurofusion jet experiment has achieved 70 megajoules of fusion yield in 2023, and that's very impressive, you know, with DT fuel and moving forward. But unfortunately, you know, politics enters into these sorts of things, and because of Brexit, everything got delayed, and they're, I think, very unfortunately terminating the continued use of jet, especially with the delays that ITER is facing. This is a most unfortunate development, but I should make a side comment, but you know, the competition with China is such they are not going to be deterred by this, and so the Western world has got to get their act together and move forward a little better. So with respect to the other images here, with respect to ITER, this has been under construction for some time, and it targets a burning plasma that, again, first plasma will come in around 2035, and eventually the goal here is to achieve a gain of 10. What does a gain of 10 means? That means the amount of energy that's put into the experiment, the amount of energy that comes out will exceed it by a factor of 10. And what does this mean? And when people ask me that question, it's roughly equivalent to demonstrating what the Wright brothers achieved in aviation at Kitty Hawk. Basically, the plane will fly. It doesn't mean that, you know, that you're going to replace trains and boats and things, but it's a major step forward. And so achieving a fusion gain of 10 is an achievable, understandable goal. Meanwhile, billions of dollars are flooding in from the private sector, but the cautionary here is that the billions of dollars that come from the private sector, there's a tremendous amount of over-promotion, if you will. So you have to be real careful. This could be a two-edged sword, and if you overpromise things and say, oh, we're going to put fusion power on the grid in 5 years or so, that it's not very believable, and you really have to validate what it is that you're doing. So while this is welcome and adds to the enthusiasm, you have to be realistic about what you can actually deliver. So, okay, this is getting back into basically what are you going to actually do, you know, with these AI machine learning approaches. And here, this is kind of a machine learning workflow, if you will. And what you see here, you know, in the different colored boxes here, you start out with identifying, you know, the measured signals in the experiment. This has been going on for a long time. You carry out your predictions based on this. This is a multi-dimensional time trace signals that you're working with. You then have to arrange these things. You pre-process the data that you collect with advanced diagnostics and such, and you arrange them in a sequential set in patches of equal length of training. And then what do you do with that? You can't have a Tower of Babel sort of situation. You have to normalize things. And so the numerical scale should be of order unity instead of, you know, all over the place over many orders of magnitude. You can do this. For example, a numerical scale of order unity could be achieved with, it's all database with all the signals, all these multiple signals, temporal spatial signals, divided by their standard deviation. Then you achieve the order of unity sort of metric. Then the blue box here, is important to concentrate on, but it's a little bit difficult to absorb all the details of this. And basically, you're dealing with all the available data that's collected that's legitimate. You can't just be throwing things out because it doesn't fit your theory or basic ideas. And it's arranged in these so-called LSTM, or long short-term memory networks, and evaluated using this receiver operating characteristic approach. I don't want to go into the details on this here, but it's covered nicely in this book by Francois Cholet that I use in my classes at Princeton, and it's widely read. It's called Deep Learning with Python, you know, one of the modern languages. It's a powerful, it introduces a powerful so-called Keras library where you understand things via intuitive explanations and practical examples. So I recommend that highly to people that want to get into this a little bit more. So then to complete this, you use the model for prediction, and you do what I mentioned earlier in the SIDAC sort of chart there. You apply the machine learning, deep learning software on new data, and you go through the VVUQ sorts of cycles to make sure that these things are actually moving the needle forward. And a good metric for that is if you start something today and you take a look and see, well, how much did you really move the grand challenge forward in 2 years, 3 years' time? And you better have an explanation for why, because there's a tremendous amount of effort going into this area, and if you want the different governments and agencies to keep funding you, you better be able to demonstrate real tangible progress. So, so this is a nice graphic of what was achieved with these AI deep learning approaches in this article that was published in Nature. It has generated well over 300 Google citations already. I recommend that to you if you want to see more of the details of all of this. It introduces so-called fusion recurrent neural network software using convolutional neural nets and recurrent neural nets. And you had to do this with powerful supercomputers. And that's why we're here at this conference to talk about aspects of this. And so in order to do all of this, what does it deliver? It delivers, basically you're using huge amounts of space-time data that came from the Joint European Torus and also the General Atomics D3D experiment in the US. And we demonstrated this, the editors of Nature are very strict. They also wanted to demonstrate that you're not doing it just on one device. You must be able to demonstrate transfer learning. What does that mean? That means that all the hard work that you're doing on one machine, like on D3D and on JET, it's transferable back and forth. Why is that important? Because then you don't have to redo everything again and go through all sorts of details every single time you encounter a new machine. So this other advance here is extremely important, led by my young colleague who is now back in China, Gedong. This is a deep learning so-called surrogate model. What is a surrogate model? It's a very fast approximate model that can deliver real-time capable sorts of predictions based on first principles theory to guide it. And why is this important? Well, if you carry out these capabilities, it's a crucial issue of realistic surrogates for future fusion systems. Why? Because if there are no ground truth measurements that you can, have a lot of confidence in going through the data at, for example, like on JET or D3D and such and other machines around the world, you still need to project forward on machines that haven't been built yet, like what I mentioned earlier, like for ITER and the so-called fusion pilot plants. And so this is extremely important, and this is a very important advance going forward. So, so a few words about this. Real-time advances, what do I mean? That means you're moving away from just archival publications that you can spend a lot of time studying carefully, but you bring this into the real world, you bring this into real time. And this also attracts the attention of a lot of advanced major companies like NVIDIA, Microsoft, and so forth, which are dealing with real-world applications in real time, like self-driving cars, drones, and so forth. So this is extremely important, but the other aspect of this is that people also want to know from a scientific basis, how do you understand, what the hell is machine learning really doing for you? What's the level of understanding that can be achieved? This is an ongoing task. We've made some attempts at this. This is a publication that we focused on why machine learning works in, for example, these disruption prediction exercises that we talked about. And it was published in the special issue of Machine Learning Methods in Plasma Physics, a European-based journal. It's already received a lot of attention. And, but I caution people, this is not the end story. You want to continually improve the level of understanding and explainability for why this works in the real physics world. So So basically you want to move towards prediction and control of this hot plasma. And during the General Atomics D3D experiment, we studied over 200 discharges, and which were carefully diagnosed in about the May-June 2020 timeframe, and we were very happy, moving beyond the Nature paper thing that I cited earlier, that you could deploy this in real time. And what do you see from that? You can see that the characteristic execution times was less than a couple of milliseconds, which is very fast, and more importantly, it sets the stage for systematic actuator deployment. What's an actuator? Well, it's basically, it's like the arms of a robot. You can manipulate the plasma. And this is a difference, very much of a difference between the laser fusion type thing, which is very difficult to manipulate the plasma that you're dealing with. Here, in a magnetically confined plasma, it's possible to do more of this. And so this allows you to manipulate the plasma state and move it to more of a thermodynamically favorable state where the plasma will stay around a bit longer and for you to make it more compatible with what you want to achieve. So this is just a quick graphic. It shows the evolution of the sensitivity score of this General Atomics D3D specific shot number. On that vertical scale here, you see all the different things that are important to measure that impacts the explainability, if you will, for why you're manipulating the hot plasma. And this shows the time traces as you're going forward. And so this gives you a nice relation of the physics-based signals to machine learning predicted disruption scores. Is it the end story? No, you have to keep on doing this to get better understanding as you move to other devices and things as you're going forward. So this is an interesting illustration of the surrogate model that I mentioned that we developed. It's a more of an approximate model, but the big deal on this thing is that you can execute this in real time. And you can do this much faster than you can run the first principles-based huge exaflop relevant big simulation codes, because those things are too slow. You can't wait around for these things to happen. You need surrogate models. And so I don't have time to go through the graphics of all the different details of that, but this particular tool, it established with workflows of neural network-based surrogates of the experimentally validated first principles electromagnetic toroidal fusion code, the so-called GTC code, which is a great code that runs on the big exaflop machines like Frontier and so forth, but it's too slow, okay, if you want to use it in real time. And so we train this with extensive simulated data from GTC, enabling realistic inference predictions of the plasma stability properties as you move forward. And here's the thing that's important, that this surrogate model satisfies compatibility requirements of a plasma control system and delivers inference times on the order of milliseconds. This is what you want to do. You want to be able to manipulate the plasma. And this will deliver results 5 orders of magnitude faster than the mainline huge exaflop code runs on the big machines like the Frontier and other systems. So anyway, this is a significant advance forward. I'm switching gears a little bit because everything is cross-disciplinary, and the old way that people think about, well, this is theory, this is experimental design and measurements, and this is engineering and so forth. Everything is more cross-disciplinary these days, and you better be able to demonstrate the connections between these things. And so this is what we call an AI-enabled fusion digital twin for engineering design. And this is a very interesting thing that was achieved with the excellent cooperation with the General Atomics D3D facility, but also with a huge amount of investment and also time from NVIDIA. They provided some essential tools that enabled us to carry this out. You start out by looking at the straightforward sorts of engineering CAD files, engineering sort of exercise from which they built the basic experimental device. And that's shown over here that you take the shot data, you feed it into the early stages of the plasma development, and you can move just that much forward. And there's a lot of work done in this area. But the yellow box up top here is what we've been actively engaged in with our NVIDIA colleagues. And you include the gyrokinetic tokamak simulations, you train it and such, and you deploy the surrogate model into the NVIDIA Omniverse device, which is pictorially shown here. And basically, the visualization gives you, picture tells 1,000 words sort of thing, and you can see it, but you can also see this move forward in real time. And that's really very, very compelling to be able to do that. This is kind of a, more virtual reality type thing, and it's not a strange sort of idea or anything at all, because, actually, the evolution of using virtual reality type capabilities like this is very familiar in the medical profession. Any surgeon will utilize these things before they go into the operating room. And so similarly, before you run a big, complicated, expensive experiment, having something like this is very useful. It's not a substitute for reality, but it certainly helps you with the training. So, okay, this, hopefully we can get this thing to actually display. This is the, okay, here, you can see it. This is kind of early results from the Omniverse capability, and what you see this is the actual live plasma as it moves through the different field lines that's keeping the hot plasma confined. This is just like an earlier stage of this. We haven't included moving the actuators around to change the plasma state, but this is a very active area, and our goal here is to utilize this in the actual control room as a additional device that will help plan the experimental campaigns going forward. So this is a very exciting development thing. It's very active, and people around the world are also very much using this, not just for advanced tokamaks, but also for other exploratory devices like spherical toruses and stellarators and so forth. So let me move forward to a separate topic. This is an international activity called the Trillion Parameter Consortium, and what they focus on are foundation models. And what are we talking about here? Basically, you're targeting validated scientific and engineering advances driven by exascale computing together with modern statistical methods featuring AI, deep learning, machine learning, but it all, and I keep on coming back to this theme, it must be properly validated, VVUQ, to establish credibility. So the foundation model efforts have especially promising potential for impact because you're examining other things, not just in the physics arena, but in others, like natural language processing, image recognition, where there's been huge successes. And there's important lessons learned from that too, because the LLM community and such, they were very open with sharing their data early in the going, and the scientific communities, including the ones in fusion research, could learn a lot from that and making their data a lot more available, having a lot more smart people being able to engage it. And so basically what we're doing here is you train these multi-billion parameter models on a mix of experimental and simulation data with technology leading to fine-tuning of huge models multiple times. And you eventually come up with smaller distilled models for multitask learning for complex and diverse, what do we talk about? Control needs, right? So you definitely want to move forward on that. It's very exciting. Because of all of the publicity over over GPTs, we named our exercise here a fusion GPT, and it's a current 1.5 billion parameter foundation model. There's some details shown here, which I won't go into specifically, but there's in fact a special session here at this conference on Friday morning that will talk about this, and there's a lot more interesting work in this area moving forward. But let me move forward a bit here. I'm getting close to the end, so leaving a little time for some discussions and Q&A. So this is a slide that really focuses on where we're going, okay? What are the future objectives? Clean energy fusion and other major grand challenges like climate are true 21st century grand challenges. They are connected in certain ways, and and it's all accelerated by the multidisciplinary R&D and the exciting new HPC capabilities that I'll mention here. In particular, validation, I keep on coming back to that. I can't emphasize that more, because otherwise you're going to be subjected to a lot of promotion that can't be proven, okay? So validation is a large versus large ground truth observational experimental database to enable improved prediction and real-time control in what we're trying to do. And this, again, as I said, cross-cuts with the big industry interests from Microsoft, NVIDIA, and such. In fact, you know, Microsoft launched a lot of the activities that we collaborate with them on with respect to utilizing transformers. That's the T in ChatGPT. And this is very exciting in deploying these capabilities. The real-time simulators featuring the surrogate models that I was emphasizing are backed by validated first principles-based exascale class HPC simulations on the exaflop supercomputers. So that is extremely important, that you need, this is all part of your modern 21st century toolkit. That's what I tell everybody, you know. This shouldn't be mysterious to people, you know, as you're trying to make progress, you know, you develop a better and better toolkit. You know, you move from the early, you know, calculators to more powerful supercomputers. Now you have AI, deep learning. These are all parts of your toolkit, okay? And moving forward, right now, you know, a key part of your toolkit are these exaflop supercomputers. In the US, you have the Frontier at the Oak Ridge National Lab and Aurora, both of which we have a very valuable experience utilizing, and there's still things to be developed in that area. And leading the way in a lot of this, I'm also involved with the major activity in Switzerland, the Alps 5,000 superchip Grace Hopper system. It's a very exciting system and has tremendous advantages. And still upcoming is this Jupiter exascale system in Germany. So industry engagement is crucial. The Microsoft transformers that I mentioned, the NVIDIA superchips powering these HPC Alps system, and the visualization capabilities like Omniverse and others that are being developed. The essential role of AI in advancing, that advances emerging ideas from the natural language processing and image recognition foundation models that led to, you know, our studies with Fusion GPT is very exciting and stimulates the engagement of a lot of super bright young people. That's a key thing moving forward. The essential role of AI here is obviously very important. For major grand challenges, the human loop aspect will likely continue to be a significant necessity as long as the VVUQ practices are properly followed. A comment here is that future realistically validated even in the quantum computing area. Quantum information science technology may well change the scenario, but you have to validate what's coming out. In other words, what is the quantum advantage that you can demonstrate in different classical application domains? So future progress demands attracting, as I said earlier, the best and brightest young talent to the grand challenge growth areas. And you do that by what? It's really a new business model going forward. It's not just the great universities like Harvard, Stanford, Yale, and such, ETH Zurich leading things. It's the combination with major labs that built the machines so you can do the validation of, and industry, strong industry engagement from NVIDIA, Microsoft, Google, and so forth, Hewlett-Packard, and so forth. And this serves a tremendous attractive purpose in getting the very bright young people to be much more engaged, because these days they have tremendous choices. And to be able to be engaged in this, then industries get a look at them, they get a look at industries. This is very attractive moving forward. So my concluding comment is that the delivery of promise from AI for science will require multidisciplinary R&D, industry partnerships, and strategic new international collaborations, featuring, for example, the very exciting ALPS system in Switzerland, and looking forward downstream, this Jupiter system, Exaflop system in Germany. So the US can benefit tremendously from more collaborations of this kind, but to keep in mind, we have to be very cognizant of what's going on here. This is the paradigm that everyone should be following, and this is the great Richard Feynman, who's a great theoretical physicist involved in the Manhattan Project and so forth. And he makes a very simple statement, which is displayed at Los Alamos. And it just states very simply, it doesn't matter how beautiful our theory is, it doesn't matter how smart you are, if it doesn't agree with experiment, it's wrong. And this is really very, very practical lesson that emphasizes the importance of verification, validation, and uncertainty quantification. So thanks for your attention. I think I'm going to wrap up here.
While we wait for a question, thank you very much, Professor Tang, for that exciting talk in the intersection of fusion research and computational science. So we have time for one question from the audience. If not, I may have one. We work a bit on uncertainty determination in computational modeling of Earth systems. So do you see any interaction or lessons between uncertainty modeling in other domains and in this computational modeling exercise?
Yes, certainly. I mean, uncertainty quantification is a huge area that modern technology can really, really contribute to. And the activities that we're doing in our application domain will cross-cut with others. And uncertainty quantification, I'll just re-explain, it's just applying statistical uncertainty methods where you don't know everything perfectly, right? And you're doing sensitivity tests and things. And it would be extremely difficult to do this, very, very rapidly. And the tools, the modern toolbox that you have is much more powerful these days. And so I think that's a huge area of growth that's going to go forward.
Lovely. So with that, thank you very much again, Professor Tang.